Okay, hi everybody. Welcome to class. Today we're going to be focusing on the final of our gas laws, which is called the ideal gas law. And as you can see, it is represented by the equation P times V equals N times R times T. So at this time, you're going to respond in the Ed puzzle. What do you think all those variables stand for? Okay, so you probably figured out that pressure is P, volume is V, and temperature is T. But N, you might not have known, was moles, and R is our new thing called a gas constant. All right, so all of this equation is based on the tenets of the kinetic molecular theory, which states that gases are made up of particles, they're in constant motion, collisions between them are perfectly elastic, their volume is insignificant, there are no interactions between the particles, and kinetic energy of the particles increases with temperature. So the ideal gas law is literally a relationship between pressure, volume, temperature, and amount of moles. We are going to be using the ideal gas constant of R is equal to 0.0821, and the unit label should be written as liters times atmospheres over moles times Kelvin. So that should be the denominator then. And then, of course, our N is moles. All right, so you didn't think we could go very long without talking about moles, did you? All right, here we go. So pressure times volume is equal to moles times gas constant times T. Pressure must be in atmospheres. Volume must be in liters. Temperature must be in Kelvin. And so let's take a look at an example here. So on this example, we need to make sure that we have pressure in atmospheres, volume must be in liters, and that literally does mean that if I have milliliters, I have got to divide it by 1,000 to change it to liters, and that if I have Celsius, I have to add 273 to get Kelvin. So let's see what we have here. This question is asking us how many moles, that's our unknown, of oxygen will occupy a volume of 2.5 liters, that's okay, and a pressure of 1.2 atmospheres at 25 degrees Celsius. So I'm going to have to add 273 to this, giving me 298 Kelvin. So here all I'm really going to have to do is plug everything into my equation. So I have my pressure, which is, and I'm going to do it up here so we can make the connection here. So I've got my pressure, which is 1.2, and I'm going to multiply it by my volume, which is 2.5, and I'm going to have moles times the R constant, and let's remind everybody that R is 0.0821. It is a constant value. Its unit label is liters atmospheres over moles Kelvin, so you must use atmospheres, so 0.0821, and our Kelvin, as we just said, was 298. So our math literally is going to be 1.2 times 2.5 divided by the product of 0.0821 times 298. And that is going to give us our moles. And when we do our moles, we will get 0.36 moles of oxygen, just like that. So it's a pretty easy equation to use, given the fact that all you really have to do is plug things in. The hardest thing is to remember that you must use atmospheres, liters, and kelvins. Okay, so let's take a look at Avogadro's law. So many times we have to think about gases in terms of chemical reactions and what volume they take up, and moles, as you've already figured out, have come into play. So Avogadro also studied moles of gases, or gases in general, and he studied them at STP. And let's remind you that that means we have a temperature of 0 degrees Celsius and a pressure of 1 atmosphere. And so that's going to be very important, because when we have that set of conditions, we know that the gas is going to take up 22.4 liters of space. Literally, that means molar volume is 22.4 liters per mole. Okay, so that also means that 22.4 liters of a gas at STP also has 6.02 times 10 to the 23rd gas particles inside it. All right, so how do we convert? If we want to know the liters, we are going to multiply our moles by Avogadro's number to get liters of a gas. And the opposite, as you're going to see, is also true. So the example here is What is the volume in liters of 0.600 moles of SO2? So multiply by molar volume. Remember that this is part of the denominator here. The moles will cancel and we'll be left with liters, just like it shows. So to find liters from moles, you multiply by the molar volume. All right. Then what about the opposite way? Does that work as well? Then to do the opposite way, in other words, we are given liters and we want to know the number of moles. So we're going to divide the given volume in liters by 22.4, so molar volume. And so you see that here as well. The liters end up canceling out and that we end up with a value of moles. So this can be done one way or the other, just depending on what you need to be able to solve for. So let's take a look at some. Well, what about if we have a chemical reaction going on? And you know, we always have chemical reactions going on, and we already learned that we can be given some grams and solve for grams of something else in a chemical reaction using that equation, so using a mole ratio and using our formula masses of the given and the unknown to be able to convert. When we want to solve for liters, all we have to do is change our formula mass in the calculation to our molar volume in the calculation. And this all depends on it being at STP. So it's got to be at STP. And remember, that means 0 degrees Celsius and 1 atmosphere. Okay, so let's take a look at what something like this might look like. Let's go look at this. It says in the following chemical reaction, chlorine gas reacts with hydrogen gas, that should say gas, to make gaseous hydrogen chloride. There is our balanced equation right there. And we have 200 milliliters of chlorine gas at 20 degrees Celsius and 2.5 atmospheres. Okay, that is not at STP. So the easiest thing to do, since we have chlorine gas and we want to know how many grams of hydrogen chloride will be produced, then we're going to have to do a two-step process. Step number 1, find moles of the given. Okay, so we have to find moles of the given, and you might be going, oh good, since I was given volume, I can just divide by 22.4, except that I'm not allowed to because this is not at standard conditions. So instead, I'm going to have to use PV equals nRT to do that. And my second step is going to be, okay, then I can do a moles to liters problem, because once I'm in moles, all I have to do is be able to solve for liters. So here we go. Let's go ahead and make sure that all our numbers are correctly prepared. So my 200 milliliters has to be converted to liters. So I'm going to divide by 1,000, giving me 0.200 liters of chlorine gas. And my 20 Celsius has to be changed to Kelvin by adding 273. So I have 293 Kelvin. And so up here at the top, I'm going to use PV equals nRT. And I'm going to plug in what I have, 2.5 atmospheres. And my volume is 0.200. My moles is what I'm going to be looking for. I am going to use my gas constant, which is 0.0821. And I'm going to use my temperature, which is 293 Kelvin. All right, so then all I really have to do then is go ahead and solve for moles, which my moles is going to come out to 2.5 times 0.200 divided by the product of 0.0821 times 293. And so once I get that, and I'm going to pause right here so that I can tell you the. Okay, so in my calculator, I got 0.021 moles of, and that is of chlorine gas. We have not converted to the HCl yet, that is just of chlorine gas. And so my 0.021 moles of chlorine gas is going to be my given then. And now I'm going to be able to use my mole ratio, which was 1 mole of Cl2. Here it is, 1 mole of Cl2 to 2 moles of HCl. Here it is right here, 2 moles of HCl. And I'm going to be able to use molar volume, which is 22.4 liters, because that's equal to 1 mole. And when I do my math, that is going to be 0.021 times 2 times 22.4, and I get 0.93 liters of HCl. And so that is my answer that I am getting at the given amounts there. So 0.93 liters. And that's all I really had to do with that. All right, so you might already be going, okay, things are getting really complicated. And that's why we're going to work through this next set of problems, just so that you can get a good example of it. And then you're going to be required to finish the rest of the problems on the practice sheet that I have assigned there. So let's take a look here. The industrial production of ammonia proceeds according to the following reaction. So there's our reaction. First question says, what volume? So we're going to be looking for volume of nitrogen at STP is needed to react with 57 milliliters of hydrogen at STP. Okay, so STP means I'm not going to have to use PV equals nRT. All I have to use is molar volume. So that's how I'm going to set things up. I am given a volume of 57 milliliters, which is the same after I divide that by 1,000. That's the same as 0.057 liters of hydrogen. So I'm going to start with that. 0.057 liters of hydrogen. And I'm going to use molar volume, 22.4 liters of the hydrogen. And that's because it would be equal to 1 mole. So I've converted to moles of hydrogen. Now I'm going to use my mole ratio, which is 3 moles of hydrogen. And I'm going to solve for nitrogen, which means I have 1 mole of N2. And I'm going to end up solving by multiplying by 22.4 liters of nitrogen at the end. Now, some of you might already be going, okay, 22.4 in the denominator is going to cancel 22.4 in the numerator, so we are not going to need that at all. In fact, all we really have to do is have our 0.057 liters multiplied or by 1, which I'm not going to show, and divided by 3. And so when we do this math, we have 0.057 divided by 3, and we get 0.019 liters, come on, of N2. And so that is a beautiful thing when we have the, we don't actually have to use 22.4. I'm going to keep showing it as we go along, but as you're going to see, you really only have to convert it using that mole ratio to figure it all out. So let's take a look at the next one. The next one says, what volume of NH3 at STP can be produced by the complete reaction of 6.39 times 10 to the 4 liters of hydrogen? Okay, so on this one, we are given 6.39 times 10 to the 4 liters of nitrogen, and we're going to use 22.4 liters of nitrogen, and that's equal to 1 mole of nitrogen. And I'm going to use my mole ratio, which is 1 mole of nitrogen, and we're solving for NH3, and that has a 2 in front of it, so 2 moles of NH3. And then finally, of course, we're going to end up using the multiplication of 22.4 liters of the NH3 to finish, which, as you know, 22.4 will cancel. So really all I end up with is 6.39 times 10 to the 4 times 2 for my answer, because it doesn't have anything else. Let's see here. Oh, did you guys notice I made a mistake here? This should be hydrogen, and that means this should be hydrogen, and that means this cannot be a 1. It has to be a 3, so that should be a 3 there. So this should be divided by 3. I'm sorry for that mistake, everybody. So 6.39 times 10 to the 4 times 2 divided by 3, and I end up with 4.26. times 10 to the 4 liters of hydrogen. So that's what we get for our answer. And so then it says, what volume would this gas occupy if the pressure, and by this gas it means the answer gas, this gas right here, if the pressure increased to 780 millimeters mercury and the temperature decreased to negative 20 degrees Celsius. So what we had before was a volume from the previous problem of 4.26 times 10 to the 4 liters. And we had remember this was at STP, so we had a pressure of 1 atmosphere, and we had a temperature of 0 degrees Celsius, which is the same as 273 Kelvin. Our atmosphere, as you know, 1 atmosphere is also equal to 760 millimeters mercury. And then what we're doing in essence is we're changing to a new volume if our pressure is changed to 780 millimeters mercury and our temperature is changed to negative 20 degrees Celsius plus 273, which means that this should be 253. So our temperature is 253 Kelvin. All right, so I'm not noticing that anything really has changed except that I have 3 conditions, volume, pressure, and temperature, changing to 2 new conditions and solving. So I'm going to use the combined gas law, which if you guys remember was P1 times V1 over T1 is equal to P2 times V2 over T2. So I'm going to plug in all my numbers. I have 4.26 times 10 to the 4 times the volume, oh, that was my volume, times the pressure, 760, divided by 273 is equal to the new pressure, 780, times the volume, that's what we're looking for, over temperature 2, which is 253. Now, you are going to end up having to multiply 4.26 times 10 to the 4 times 760 times 253 and divide by the product of 273 times 780. And so when you do that, and I'm going to do that real quick on my calculator, 4.26 times 760 times 253 divided by 273 divided by 780. And I get 3.85 times 10 to the 4 liters as my new answer. So that's going to be my new answer. Well, how did I know to do that? Because what I had there was a volume with its pressure and temperature getting changed. And so that fit very well into the combined gas law. It didn't have, I could have gone back and changed it back just to moles, and then I could have converted it to the new pressure and temperature, but I already had a volume, and so I thought it would be the easiest thing to go back to the combined gas law. So let's take a look at C. It says I have 20 moles of nitrogen, and it's available to react. What volume of NH3 at STP can be produced? Okay, so the first thing I want to do is recognize that this is already at STP, so I don't have to use PV equals nRT. I can just set this up as a moles to liters problem. So I have 20 moles of nitrogen, and it's still up here in this balanced equation, so I still have 1 mole of nitrogen, and this is going to be to 2 moles of NH3, and then all I need to do is use molar volume, 22.4 liters of NH3, and that's because that's equal to 1 mole. So my calculation here will be 20 times 2 times 22.4, and when I do that math, I get 896 liters of NH3. Okay, now that one was a pretty straightforward one. That's because everything was at STP. Let's take a look at D. What volume of H2 at STP will be needed to produce 800 liters of ammonia measured at 55 degrees Celsius and 0.9 atmosphere? Okay, so here's the thing. If I need to know the volume of H2 at STP, but I am starting with a volume that is not at STP, I'm going to need to convert this to moles so that then I can just solve for H2 at STP using molar volume. So the first thing I am going to use, number one, is going to be PV equals nRT, so I can just find the moles. And then I can do a mole, part two, I'm going to do a mole to liter problem at STP. So my pressure is given as 0.9 atmospheres. My volume is given as 800 liters. I am looking for N. My R is 0.0821, and my T is 55 plus 273. So 273 plus 55, I should be using 328. When I do my multiplication and division, my number of moles, and this is my number of moles of H2, comes out to being, let me do the math real quick, 0.9 times 800. I am getting 26.7 moles of H2. And so if I just wanted to know, well, how many moles of H2 is this? That's what I just did. And that's why I asked that question, how many moles is that? So now I can start with 26.7 moles of H2. And I can just use my mole ratio, which is 3 moles of H2 to 2 moles of NH3. Oh my goodness, this is not H2, everybody. This is NH3 itself here. So that's going to mess me up, and that means this doesn't have an answer yet. So hang on. This is NH3. So there should be a 2 moles here and a 3 moles of H2 here. And then we just need the molar volume, which is 22.4 liters, because that's equal to 1 mole. So my calculation will be 26.7 times 3 times 22.4 divided by 2. And doing that math, I get 897 liters of H2. Okay, cool. I've gotten that answer. How many moles of H2 is this? All we would have to do is take our 897 liters and divide it by 22.4. So 897 divided by 22.4, and that's going to be 40. Comes out to 40.05, so 40.0. All right, so the reality of this is that these are challenging problems. So I'm going to ask that you give a try to some of those other problems. These are problems that make the distinction between on-level chemistry and the honors level chemistry, and ultimately, of course, the AP level later on. So give those a try, turn in what you can. Thank you, everybody.